So section 4.2 is going to continue our introduction into probability, and in particular, this is sort of a look back at our complementation rule. It's asking you what is meant by probability of B or B bar equaling 1. And let's think about that a little bit. Remember, in terms of the complementation, what that means is that you've got two possibilities and you're looking for the probability that one of them happens. So this could be our sample space. And something's going to happen. It could be event B here. Oops, not event B bar. How about event B? And then the other part of this would be B bar. So you're one or the other. So the question is, what is meant by probability of B or B bar equals 1? Well, they give you four possibilities here, and let's see which one of these makes sense in terms of an answer. This comes directly out of your homework, so really giving you one of the answers to your homework. When randomly selecting an adult, let B represent the event of randomly selecting someone with blood type B. Write a sentence describing what the rule of complements below is telling us. Probability of B or B bar equals 1. Here are your choices. A, it is certain that the selected adult does not have blood type B or have type B blood. Second choice, it is certain that the selected adult has type B blood. C, it is certain that the selected adult has type B blood or does not have type B blood. And finally, it's impossible that the selected adult has type B blood or does not have type B blood. We can get rid of that last one. Why can we get rid of that last one?
Impossible. It has to be one of the two.
If it's impossible, what probability do you associate with impossible? 0. And the probability that they list there is 1. So we can rule that out right away. Now, if you look at the first one, it is certain that the selected adult does not have type B blood. That's not all what's being said up there. It is certain that the selected adult has type B blood. I don't know. There's more being said. How about the third one? Gerald, I think you were...
I would say it's C, right? Because
Yes.
it has to be one of the two, and one means that it's certain, right?
Yeah.
That's a certainty.
Exactly. So basically what they're saying is that you either have type B blood or you don't have type B blood. And it doesn't matter if you have type A, type AB, or type O. You're type B or not B. That's all it's saying. So yes, good job. Thank you, sir. The correct answer is C. So yeah, let's put a little star there. Now we're going to start working towards calculating more and more probabilities here. We'll start with this one. And let me see if I can't zoom in a little bit, make that a little easier to read. This is data that comes from drive-through restaurants. What happens when the book goes from a physical copy to the electronic copy is that they denudor all these problems. If you actually look at the physical copy of the book, these restaurants are probably McDonald's, Burger King, Taco Bell, and maybe Kentucky Fried Chicken, not sure. But we want to look at the probability. If one order is selected at random, find the probability of getting a food that is not from restaurant A. So I'll start out by making a little definition here. And let's let A be the event. The food is randomly selected from restaurant A. So that's our event. But that's not exactly what we're being asked for. If the order is selected, find the probability of food that is not from restaurant A. So what probability should I write here? P of what? Yeah, well done. P of A bar. Now there's a couple ways I can calculate this probability. One of them is kind of directly. Now I'm not sure if this is clear or not, but these are the marginal totals. So there's a total of 1,134 orders in this survey. So 1,134. And of that 1,134, let's add up the ones that come from something other than restaurant A. That'd be 325 plus 286 plus 161. So what's that probability? Well, it's great question. Why did I leave out 362?
Because those are the orders that come from.
Yeah, yeah, exactly. It's everything but A. One of the probability of getting something that's not from restaurant A. So that's why we did everything but A. So not from restaurant A. What was that total? 772. Okay. Now that's one way you can get this. There's another way that might be a little bit more efficient. Can anyone think of what that other way would be? If you're thinking of the complement rule, then I applaud you.
1 minus probability A.
Yeah. The other possibility is I could do that as 1 minus the probability of A. The probability of A is 362 over 1134, and I'm going to subtract that from 1. And when you do, yeah, you have to get common denominators and such. That's fine. You'll end up with 772 over 1134. You're going to get the same thing. Beautiful. Now this does reduce into lowest terms. If you wanted to write, 386 over 517 or whatever that, or 500, maybe 567, that's fine. Again, I'm not worried about you putting it in lowest terms. Your calculator can help you out in this kind of a case. If you have a graphing calculator, if I did 1 minus 362 divided by 1134, I'm missing this terribly. Let's try again. 1 minus 362 divided by 1134 gives me a decimal value. Sometimes I'll take decimal values. More often than not, I'm happiest with fractions. If you hit the math key and then press enter twice, it'll turn that into a fraction. And as a bonus, it also puts it in lowest terms. So great. I don't care if it's in lowest terms or not. I want to make sure you've got the right answer. Okay. Let's move on to the next one here. What's the probability of getting an order from restaurant A or restaurant B? So basically this, what's the probability of A or B? What's that probability going to equal? Well, we could do it like this. Yeah, let's see. Maybe
687 over 1134.
Oh, well done. So in terms of the number of possibilities, you could do it like this. There's 362 choices for restaurant A plus 325 for restaurant B over 1134. So 687. Coincidentally, in this one, it's also equal to the probability of A plus the probability of B. If you calculate it like that, you would get the exact right answer. But that's not always going to work. Let's see an example where it doesn't work. Now I need some more notation here. What's the probability of getting an order from restaurant A or getting an accurate order? So if they get an accurate order, they got it right. So I'm going to let R be the event of an accurate order. Because this down here is asking us for the probability of A or R. All right, let's see about that. Now, the way we calculated things up here was just to add those probabilities. So the probability of an accurate order, let's see if I can get away with it this way. Probability of an accurate order is, probability of A first and then a probability of an accurate order. Probability of, I keep on doing an R. Probability of R. Let me mute somebody here. I don't know, somebody's unmuted that should be muted. Where's the mute all button? All right. Let's keep going. Probability of A, that's going to be 362 over 1134. What's the probability of getting an accurate order? You can't just look at the bottom totals anymore. We've got to look someplace else. 989 over 1134. You see something wrong? Well, if you subtract the 362, then you're leaving out the people that ordered restaurant A, or at least some of them. I counted some of them. I mean, you are seeing something that looks alarming here. Let's take a look. Let me finish this calculation, then we'll look back and fix it. So let's see, we've got 362 plus 989. That gives me 1,351 over 1134 for the probability. I joked earlier that if you gave me an answer like this, I thank you ahead of time, because you're making it very easy for me to grade. No partial credit, just wrong. What's clearly wrong with this?
It's greater than 1.
It's greater than 1, yeah. So if you see something that's greater than 1, you know it's wrong. It'll just never ever happen in this class that you get a probability greater than 1. It shouldn't happen at all. Probability of 1 is as big as they get. So what went wrong here when we did this? Now somebody was saying, well, didn't we already count somebody? And the answer is yes. Let me take a look at this and let me rewrite it over here. Here's what we did. We calculated the probability that somebody was in A. So we added up all these. And then we said, all right, well, there's also a possibility that they got the order accurate. And so we added up all those. Can you see what happened when we added those two probabilities? Yeah, we did some double counting. So what you're going to need is what's called the general probability rule. And it's a probability of A or B. There's a probability of A plus a probability of B minus a probability of A and B. So you got to subtract that double counting. So if I do that, here's how it would look. I'll get 362 over 1134 plus 989 over 1134 minus the probability of, I wrote A and B here, but it's really for us is going to be A and R, minus the probability of the intersection. What's the probability that somebody got an accurate order at restaurant A? 330. So somebody was kind of hinting at this earlier, and you're exactly right. What you want to do is remove that double counting, and that should give me a probability that at least is between 0 and 1. So 362, actually, you know what, you can just do this, 1351 minus 330, minus 330, I should be able to do that in my head, my bad. 1,021 divided by 1,034. At least that passes the smells test, right? It doesn't look bad because it's between 0 and 1, and that is indeed the right answer. Bravo. That's where these two things overlapped. That's where you had an accurate order and it was from restaurant A. Because what happened with this, why it was wrong initially back here, is that you had that double counting as we added up everyone here and then we added up everyone here. But if you look at that number where they overlap, the accurate orders from restaurant A, those were counted twice. So you subtract them off once. And that's what we're doing here. Beautiful, beautiful. Let's call it a day here. We'll finish up the rest on Monday.